Okay guys, what I want to do is I want to show you guys a very, very cool formula that you can use almost in any physics, mechanics problems, okay? The only time you cannot use it is with collisions. Okay, so when we do collisions, there's one of two formulas that apply. When we do collisions, it's either preservation of momentum, and who can tell me what is the law of conservation, not preservation, sort of. Okay, conservation. What is the conservation of momentum theorem?
Isn't that energy cannot be destroyed? No, that's the one.
The total linear momentum is the total
linear momentum of an isolated system is conserved.
Where I don't know, external forces acting.
What about the total momentum?
It's conserved.
It's conserved.
Just before collision, after collision.
Right. So in other words, we write it like the total momentum, that means the sum of momentums before, so in other words initial, is equal to the sum of momentums after. Okay? So that is conservation of momentum. It is actually very easy. If you've done the questions on the course, if you can do them, they really cover all of the type of questions that you really can get. The next one is elastic collisions. Okay, so an elastic collision. Who knows what an elastic collision is?
When kinetic energy is conserved.
That's when kinetic energy. Now, conservation of momentum is a universal law. It always applies. Okay, an elastic collision is the conservation of momentum still applies.
Is that equal to something?
But in an elastic collision, the sum of my kinetic energies before is equal to my kinetic energies after. Now you need to know that momentum is mass times velocity, and then you need to know that kinetic energy is half mass times velocity squared. So you'll take every element in that system, mass times velocity, add them together before, add them together after, and it has to be equal, always has to be equal in an isolated system. An elastic collision is if they tell you it's an elastic collision, then you take half mass times velocity squared for everything, and it has to be equal, okay? So that is in collisions, we use these theorems, but the formula that I want to show you, you actually know it very well, but no one is using it, so I'm going to focus a little bit more on it and show you how you can use it in almost any system. Okay, that is this formula that the net work done is equal to what? This is the work energy theorem.
It's friction work, it's force times distance, isn't it?
Yes, but that's the definition of work. In other words, work itself, any work applied, work done by friction, work done by gravity. So I'll get to that in just a minute. But this is the work energy theorem.
Isn't it that it has potential energy and kinetic energy?
Doesn't it have cos theta somewhere?
No, it doesn't.
It does have cos theta in the original formula.
Okay.
But what is the work energy theorem?
Gosh. The network is equal to the total kinetic energy?
No, it's equal to the change in kinetic energy.
Yes.
Okay, now let me explain this to you guys. It's not difficult. It's really, really, really simple to understand. Okay? I'll explain it like this. Where do we use the concept of net very regularly? What does net mean? If I talk about something, a net, where do we often use that concept?
With forces.
Outside of physics.
Besides physics?
No.
Isn't this coming from internet, this net?
I don't mean to laugh. No, you're 100% right.
There's this other message I got from what it's like I was getting free ATM. It said surf the net.
Surf the net. You're 100% right. That is called. It's the internet is shorthand called the net. So you are right, but that's not what this word is referring to. Net. Can you think of a place where we often talk about net? Something. Net never comes on its own. It's net something.
Network.
Okay, wait. Let me answer. Let me answer because you guys are going to embarrass yourself soon. No, but this is funny. Network done. Anyways, no. Net. Have you ever heard of net profit? Net income.
Oh.
Net. Now, what is net
Financial.
income? What is your net income?
The total income.
No.
No, I mean total profit.
It's profit. Net income is your profit.
Mm-hmm.
Now, what does that mean? What is profit?
What you got initially extra.
Sorry?
Yeah.
What
What
did
you
say?
got extra from the original amount. So what you.
Almost. It's what you get extra. What you do is you take your income minus your expense. Does that make sense? So let's say my income in a month is 10,000 rand, but all my expenses add up to 8,000 rand. Then my net income is 2,000 rand. My profit is another word for net income. So net talks about what you get in minus what you get out. So when we talk about net work, work is the ability to convert energy. Okay, so you can think of work as energy that's being converted. Okay, so think of work as energy. So if I talk about the net work done, it's talking about the energy that is left. Now let me explain by drawing for you a little diagram. Let's say we have an object here that's being pushed up an incline. Okay, we're looking circle, but this thing is being pushed up an incline. What do we call the force when something is being pushed? It's an applied force. So an applied force, this is applied. Applied force is always either a rope or an engine or a man pushing. Is that how you spell engine? Or a man pushing or pulling, or it is something that's being applied. Does that make sense?
Yes.
I'm applying a force. That's an applied force. Now, if we talk about this is always an income. No, I lie. I take that back completely. Okay, this is an income energy. So when I'm applying a force, I'm adding my energy into the system. Okay. Now, it can only be an income if it's in the direction that the object is moving. You understand? So the object is already moving in a certain direction. Let's say I'm pushing the object upwards and it's moving upwards. Okay? Now, if I'm pushing in the same direction as the object is moving, I'm adding energy into the object. Does that make sense?
Yes.
Okay. So in other words, my work, the income here would be work applied. That would be one of the incomes. Now, what other forces are acting on this object?
Frictional force?
Frictional force. Frictional force is always in the direction or in the opposite direction?
Opposite.
Always in the opposite direction. So here we have frictional force acting on the object. The work done by friction. Okay, so what do I mean by the work done by friction or the work done by the applied force? Well, work itself is the formula. Any work done is that force. Whatever the force is, if it's force applied, it's force applied. If it's friction, it's friction. If it's gravity, it's what do we call the force of gravity? You don't know?
What is the force of gravity?
Yeah, what do we call the force of gravity?
It's the force that you exert due to the position of
No, the force of gravity is called weight. Weight is the force of gravity, which is mass times gravitational constant. That's the force of gravity. So, whenever I'm working out the work done by a force, I take that force and I multiply it by the distance that is in the direction of the force.
Yes.
So in other words, if this thing moves from here to there and this distance is delta x, then the force done, the work done by the applied force is the force applied times the distance over which it was applied. Okay? Frictional force is the work done by friction is equal to the frictional force. And how long is friction applied on the system? Well, for as long as it's moving on a frictioned surface. Okay? Does that make sense? So times, so that's, I'm working out the work done by friction. I take that frictional force and I multiply with the distance over which that friction is applied. But here's the important part. For example, the work done by gravity is the force of gravity, which is weight, mass times gravitational constant, times, and now it's not delta x anymore because the problem with gravity is the force of gravity is always straight down. And the object isn't moving in that direction. Do you see? It's moving like diagonal. It's not moving in this direction. So but it is moving up. It is moving in the direction of the force, but not this much. If I take from this point to that point, you see, it is moving up, but not this whole distance. The distance over which the work is done by gravity is only from here to there. So we need to find out what this size here is. What is this length? Okay. Now, gratefully, all of you have maths, so all of you should see that this is trig, and this is an angle theta, and what side am I trying to calculate?
On the opposite side.
The opposite. So I have to use opposite. What I have this length. What do I have?
Hypotenuse.
Hypotenuse. So opposite over hypotenuse is? Sine theta. So if I have theta, if I know the angle that the surface is making, then I can find out the opposite by multiplying both sides with the hypotenuse. So I get that the oh no, sorry, Bakani, you don't have maths. Okay.
No, I'm fine.
But you can remember this?
Yeah.
Okay. So there we go. The opposite side length. In other words, this length, the height that it travels, that's the only part where the gravitational force is doing work. He's not doing work for the whole distance of x. He's only doing work for the distance that he's picking it up on. If it was just going straight up, then delta x would be equal to delta h. Delta h is now the change in height. So if I was just picking it up from the bottom to the top, then my displacement is equal to my change in my height. If I'm just moving it from left to right, then my delta x is whatever, and my delta h is?
It's h sine theta.
No, 0. What was my change in height? Nothing. I didn't lift it up at all.
Okay.
So if I'm lifting it straight up, then delta x is equal to delta h. If I'm putting it straight on the horizontal axis, then delta h is actually 0. So anywhere in between here, delta h will be somewhere between 0 and x. It would be less than 0, it would be less than, greater than 0, it would be less than x. Okay, but how can we calculate it? We take delta x and we multiply it with sine theta. Okay, we take this, that's what I calculated here. Hypotenuse, which is delta x. Don't confuse this h with that h. They're not, this one is hypotenuse, that's height. But I take the hypotenuse, which in this case is delta x, That's the distance that my object is literally moving. But how high is it being picked up? That's there. And that depends on the angle. Okay, make sense?
Yes.
Is that okay? So in other words, the work done by gravity is not mass times gravity times delta x. It would only be that if I was just picking it up. It would be mass times gravity times delta x sine of theta. Okay, so now let's go and look at the work done in terms of income and expenses. Okay, I'll explain the right-hand side of this equation just now. So if I put energy into a system, that would be work applied.
Yes.
Now in this case, if I'm pushing in the same direction as the object is moving, I am adding energy, so I'm at income.
Okay.
Work applied is at income.
Income.
Is the work applied by friction, there's frictional force, is it an income or is it an expense? Will it add energy or will it steal energy? It will steal energy, so I will subtract expenses. I will subtract the work done by friction. Okay? How about the work done by gravity? Gravity is pulling down. If I'm pushing something up a hill, is gravity going to work in my favor or against me?
In your favor.
Oh, really? Let's see you push up my car up a hill. Is gravity helping you or making it more difficult to push it up the hill?
It should be helping you.
It should be helping you if you're pushing it up a hill.
Yeah.
So what you are telling me, it's easier to push it up a hill than to push it straight.
No,
No,
I'm not
it's
saying
easier to
you-
push it
it's-
straight.
I think you're taking it too general.
You think it?
You're taking it too general. As if you're pushing it, you know it's hard to push it up the hill.
Yeah.
Then pushing it straight.
So if it's harder, why is it harder to push it up a hill than to push it straight forward?
You said friction force is always opposite.
No, but let's say that it's the same road. If I push it straight, or I'm pushing it up, it's the same road. Friction isn't more. Friction is how difficult that surface is to push. Okay?
The roughness of
The roughness of the surface. Now whether I lift the surface at an angle or it's straight, friction won't change. What does change?
It's upward force.
I'm trying to push it up.
So the gravity will change.
In other words, if I push it straight, I'm not trying to lift the height. Do you understand?
Yes.
Gravity is not working against me, it's not working for me.
Yes.
It's neutral. That's this point. So what is the work done by gravity if I'm not changing height? The work done by gravity is mass times gravity times the change in height. Okay? Now change in height is delta sine x, delta x sine theta, but that's only if I don't know what the change in height is, then I'll use this. If I know what the change in height is, I'll just use the change in height.
But in this case, we don't have because we're not moving upwards.
But we do have it. If we're not moving upwards, delta h is
0.
0. So what is the work done by gravitational force?
Zero.
It's nothing. It's not adding energy. Even if I add it or subtract it, it's not doing anything to the system. Does that make sense?
Yes.
But if I'm pushing it up, is it taking away from the energy that I'm applying, or is it adding energy to?
It's taking away.
It's taking away. Does that make sense to you?
Yes.
So in other words, it's not helping me move this thing up the hill. As a matter of fact, if I let go, it will start rolling downhill. Which means if I wasn't applying a force, it would have the same effect as friction. It will be against the direction of motion.
Okay.
Does that make sense? So that means work done by gravity. Now work done by gravity can be an income or an expense. It depends on in what direction is my object moving. If I'm moving up, gravity is always moving down. So if my object is moving up, the work done will always be an expense. If my object is moving down, now gravity works in my favor. I can now put my car on the downhill. I don't even need to push, and it will start going down. Why? It's not friction that causes it to move. Friction is always in the opposite direction. What is causing it to move? Gravity. Gravity, if it's coming downhill, is an income. Make sense?
Yes.
Okay, but for this specific case, we're now looking at this specific case, we're moving something up an incline. Okay, then gravity would be an expense. Now, imagine this. Imagine I'm trying to move an object. As I'm trying to move it, I'm putting in enough energy to overcome friction. So in other words, the amount of energy that is going to be stolen by friction and gravity, I'm giving just enough energy to overcome that.
Okay.
Are you with me?
Yes.
Does it make sense?
Please repeat that, sir.
So remember, so friction needs energy. For me to push this thing, okay, I need to put in more energy than friction is stealing.
Yes.
Does that make sense? If I do put in more energy than friction is stealing on a straight road, so let's ignore gravity for a moment. If I put in more energy than friction is stealing, what will happen to the object?
Accelerate.
It will accelerate. Brilliant. If it was standing still, it will be going faster and faster and faster and faster. Very few people know that, actually. They don't get it. Okay. If I'm pushing it up the hill, in order for it to accelerate, I must overcome friction and gravity. Do you understand that?
Yes.
Okay, so what will happen if I'm making a profit? Okay. For those watching the video, I'm making inverted commas. Okay. What will happen to the object if I am making a profit in my energy? In other words, I'm putting more energy in than is being stolen. The object will
Accelerate.
accelerate. It will accelerate because what is happening with the extra energy? I'm still putting it in. What is happening?
it's
It's
not
not turning into
dominant.
heat. The thing's not catching flame. It's turning into some sort of other energy. So my energy that I'm putting in to push this thing is being converted into kinetic energy. Okay. Now, here's the one thing. So, all of the energy, so this is my profit, remember? My profit will change my kinetic energy. Does that make sense?
Yes.
In other words, if my net work done, in other words, the profit of energy I have, if that is greater than 0, then it means that my future kinetic energy will be minus my initial kinetic energy, that's the change in kinetic energy, will be greater than 0.
Okay.
Does that make sense?
Yes.
All I'm doing is I'm changing this into delta change in kinetic energy. In other words, remember what we said now, if I am putting in more energy than gravity and friction is stealing, I will be changing my kinetic energy. I will be adding, the energy will be converted into kinetic energy. And so the change in kinetic energy will also be positive. Makes sense? In other words, my future kinetic energy, just notice this is a inequality. I'm just adding EKI on both sides. And then I get that my future kinetic energy will be bigger than my initial kinetic energy. Okay. Does that mean before I started applying the force, the object wasn't moving?
No.
No, it was moving. But now I'm making it move faster. So what is kinetic energy? Is a half mass times velocity squared. In other words, half of my mass velocity squared, my future velocity squared, would be greater than half of my mass times my initial velocity squared. In other words, I can divide both sides with a half and get rid of that. I can divide both sides with a mass, get rid of that. And then I get that my future velocity squared will be greater than my initial velocity squared. Do you see? So literally, if my net work done is positive, my future velocity will be greater than my initial velocity. Make sense?
Yes.
Okay. Now the opposite is true. What if my net work done is less than 0.
Which means you'd be putting less energy to.
It decelerates.
So in other words, friction wants energy.
Yes.
It's taking some of the energy that I'm putting in. Gravity wants energy. It's taking some of my energy. But now I'm not putting enough energy in. Where is friction and gravity going to get its energy from? You understand? They require energy. Friction requires energy, and friction gets all of its energy from the applied force. Okay? So it gets all of it, so friction is satisfied, but now gravity needs energy. Maybe I can satisfy some of gravity's energy, but not all of it. So gravity still wants energy based on mass times gravity times change in height. Okay? The mass still requires a certain amount of energy to push this thing up the hill. But if I'm not putting in enough energy, where is it going to get its energy from?
From the applied.
No, I'm already using up all of my energy on friction, and the little bit that I have left, gravity takes, and he wants more. You understand what I'm saying?
Yeah,
If he wants more.
Isn't it from kinetic energy?
From kinetic energy. So this object is moving. The object itself has energy based on its movement.
Yes.
The fact that it's moving. So if I'm not putting in enough energy to keep it moving,
It's
going to start taking energy from the object itself. And what is going to happen to the object? It's going to
move in the opposite direction.
It's not going to move in the opposite direction yet.
Decelerate.
It's just going to decelerate. It's going to slow down until it reaches 0, and then probably start heading in the opposite direction. So it's going up the hill, go down. Do you see what's happening?
Yeah. Yes.
Okay. So in other words, if my net kinetic energy, if my net work done is less than 0, then with the same, I don't want to write all this out again, but in the end, the sign will just change. My future velocity will be less than my initial velocity. You see that?
Yeah.
So the same thing applies, and this is now. So this is a remarkable formula because it literally can be used in any situation of mechanics that's not a collision. You can use this formula. Projectile motion, pushing something up an incline, working out if someone dives into water. You know, remember that question?
I do. Oh my word, that was bad.
Okay, I'll show you. We'll go through control test 1. We'll go through control test 1, and I'll show you how you can almost do every single question in that paper, except for momentum, just using this formula.
Okay.
What formula? That net work done is equal to the change in kinetic energy. Now, we just need to figure out what is an income and what is an expense. So let's just look at another scenario. Let's imagine we're now pushing something down a hill. Okay, or let's say this. Let's say I'm not pushing it down the hill, but I'm in a car and I'm going down a hill and I am applying the brakes. Okay, so that it doesn't go down the hill too fast. Or you're on a bike and you're pulling the brakes so that you don't go faster and faster, so that you can go down at a slower velocity. Now, what if I'm going down a hill? Give me some incomes. What are income energies if I'm moving down a hill?
Gravitation.
Gravity this time is an income, so it will have a positive.
Yes.
What would be any more incomes? Can you think of more incomes? Is applied force an income in this case?
No.
Why not?
Because it's working against.
Yes.
It's working against motion. It's taking away from the velocity. Does that make sense?
Yes.
So we'll have minus the work done by the applied force. So if I'm pushing the brakes, something is adding a friction, like not a friction, a force. I'm applying a force. An engine is applying a force. Or do you understand that? Okay, so that's what applied force is. Plus, what is another expense?
Friction.
Friction will always be an expense. That's nice though. You can always just subtract friction. And it's equal to the change in kinetic energy. So whatever the answer is, now here's a formula. So in other words, this is not a standard formula. It's not you will always use this formula. Each scenario you'll look at in a new way.
Okay.
For example, let's think of something being thrown up into the air. If I throw something up in the air, here's the one thing that you have to keep in mind. The moment something changes, we can't use the same formula if something changes. Let me give you an example. If I throw something up in the air, here's my hand, I've got a ball. While I have the ball in my hand, just before it leaves my hand, the whole time, like at the bottom, what is the velocity?
0.
0. As I'm throwing it up, I'm applying a force to that ball. The moment that ball leaves my hand, the force that I apply is no longer acting on it. Which means there's a story now here where the ball is in my hand, and then the moment it leaves my hand, the story is now different. It's a new scenario. So we would have an initial velocity here and a final velocity there. But this final velocity will be the initial velocity for the new story.
Yes.
Do you get that? So the moment something changes, the moment a force, here's another example that we saw yesterday. Here's a ramp like that. And from here to there is horizontal. It doesn't look like that on my graph. And here there's friction, but this portion is frictionless, which means there's two stories happening here. They call this A, B, and C. So in other words, if I consider the system, I must consider two parts. This is an initial velocity, and that is a final velocity. But this final velocity is the initial velocity for this system. Do you get that?
Yes.
Okay, so the moment something changes, I consider it in a new light. It's a new story. I separate the two. And the only connection is that the initial velocity here is the final velocity of the previous story. Does that make sense?
Yes.
Okay, cool. So something is rolling down here. I didn't say that. Okay, so just with that in mind, we don't just use this formula, and this is initial velocity, and that's the final velocity. That's not how it works. Do you get what I'm saying?
Yes.
Okay, so let me quickly go on and show you how. So imagine I'm throwing something up in the air, but I'm not talking about this part. I'm talking about something is now being thrown up the air. All of a sudden it's thrown up in the air. Okay? And what are the forces? What are the incomes and the expenses while it is in the air? So while it is in the air, we call it free fall. What are the incomes and expenses of a free-falling object?
It's gravitation.
Gravitation. Is that an income or an expense?
It should be an expense.
Expense. Okay. Negative WG. Anything else?
It's normal force. Normal force.
Normal force only applies when an object is on a
Isn't
surface.
friction is also an expense?
Friction would be expense. Let's assume there's no air friction. Okay, so friction would always be an expense, but let's assume, usually with these type of questions, they say ignore air friction. Okay, so let's ignore air friction. Is there any applied force while it's in the air? No, it's left my hand. No one is touching that thing. The only force acting on it is gravity. So, awesome. Gravity as an expense is equal to what? Change in kinetic energy. Now look at how cool this formula changes. Now it changes to the work done by gravity is always mass times gravity times the change in height. Now this time we don't use that delta x sine theta because it's going horizontal.
There's
vertical.
no angle.
Yeah, there's no angle involved. It's a 90-degree angle actually. So cos theta would not apply here. Okay. So in other words, here I'm just talking about the height. The change in my height is equal to a half mass velocity squared. Now I see, oh, both sides of this have a mass, so I can cancel out the mass. Sorry, this is not velocity squared, this is in final velocity squared minus initial velocity squared. Sorry, that's the change in kinetic energy. Let me write it like this, it's probably easier for you to understand it like this. Change in kinetic energy is future kinetic energy minus initial kinetic energy. Make sense? But now I see everything has mass. So I can divide mass with every term. And I see there's the half. I don't like working with that half. Let's multiply everything with 2. And this is a negative. 2g delta h is equal to, now I multiply this with a 2 to get rid of those halves. So I get future velocity squared minus initial velocity squared. And now if I add initial velocity on both sides, then I get future velocity squared is equal to initial velocity squared minus 2g delta h. Does that look familiar?
Yeah.
Do you see? So in other words, I don't need to go and remember this formula. Now in our formula it's a plus there, but then we must use g as a negative anyway because g is downwards. Okay, so that's fine. So we'll keep it a negative here. I just want to show you, you didn't have to go and remember that formula. You just have to remember this idea. What are my income energies? What are my expense energies? And I just always equate it to the change in delta or the change in kinetic energy. Now we'll do a few examples like this and then you'll see how it works. Okay, I just want to show you some scenarios, different scenarios, and each time the formula is different, but the idea is the same. Make sense?
Yes.
Cool. What did I want to show you? Okay. Let me quickly just show you in this formula that we have here, for example, why can I use this formula to calculate anything except time and acceleration? If they ask me for time and acceleration, it's probably going to take another step. I can still use this, but it's a little bit more complicated. Let me show you. Weight done, or the work done by gravity. How did we say? What do we use for the formula for work done by gravity?
It's mg.
Mg delta h. Okay, or it can be mg delta x times sine theta, depending now on whether I have the height, the increase in height, or whether I only have the distance on that ramp. Okay, depending on that. Okay, and then what is the work done by the applied force? How do we calculate that? Okay, I'll show you. Force applied times delta x. The normal work formula. This is also the normal work formula. The work formula is my force times my displacement. Okay, but gravity force is weight. Gravity displacement is delta h. Weight is mass times gravity. Delta h.
Yeah.
Do you understand what I'm? They're all the same formula. What is the work done by friction?
Same
Then what?
as force applied.
Frictional force
Force
times delta x.
X. Yeah.
What is the formula for change in kinetic energy?
Half mv squared.
Half mv future squared minus half
mv initial.
mv initial squared. Think of any value. If they ask you to find the displacement, then there's displacement. Okay. If they ask you to find out the frictional force, there's the frictional force. If they ask you to find the applied force, you've got the applied force. If they ask you to find the mass, there's the mass. If they ask you to find future velocity, there's future. Initial velocity, there's initial. If they ask you gravity is a constant, if they ask you to find the height, there's the height. Okay. You see that?
Yes.
The only values that are not in here is t, time, and a, acceleration. You see that?
Yeah.
Okay. So those are the only ones that you can't necessarily get by this. But at the same time, they will give you all of the other values. If you don't have acceleration or you don't have time, okay, then acceleration is future velocity minus initial velocity over delta t. Or if you don't have t, then t is the time is in that formula. Well, I suppose you can just use this formula. Time is just the change in velocity. This is the change in velocity divided by acceleration, for example. Okay, so there's different ways of finding time and acceleration. We'll look at some options. Okay. The nicest thing is if they tell you this object is moving at a constant velocity. What do you know if it says it's moving at a constant velocity in this formula? If they say constant velocity, what can you then before you go into this big formula, replacing work done by gravity, then you can replace something immediately. What can you replace?
Isn't the final velocity is what your initial velocity?
Yes, in other words, final velocity and initial velocity are the same. So what will happen on this side of the equation?
It's going to be 0.
Change in kinetic energy is 0. If I'm moving at a constant velocity, it means my kinetic energy is not changing. So change in kinetic energy is 0. Does that make sense?
Yes.
For a lot of people, they don't get that. I don't think they understand change in kinetic energy. Change in kinetic energy means the difference between my future and my past. If there's no difference, if it's the same, it means it's 0. The difference between the two is 0. Make sense? Cool. Okay, I want to say as much as possible before I actually start with a question, but I think it's time. Let's start with a question. I avoided this question yesterday because I didn't think I can use my formula, and I am so confident in that formula that I say you can use it in any situation except collisions. So I'm going to test it. I have not tested it. I'm going to test whether you can use it to find tension. Okay, let's see if it works. I don't know if it's going to work. I hope it does. If it doesn't, I'm going to embarrass myself. But that's okay. I don't mind embarrassment.
That is
Okay, so here in this question they tell us a block of mass of 1 kilogram is connected to a block of mass of 4 kilogram, like that, by a light inextensible string. The reason why they mention a light inextensible is so that when something is being pulled, obviously if it's like an elastic, then even though you're applying a force, the force is not being applied to the object, it's being applied to the string. You see, it's stretching the string. So that's important. Another thing that's important is if I'm working with objects, the mass has an effect. So they would say a light string, in other words, ignore the weight of the string. It's not like a cable that you also, or a chain that maybe also is difficult to pull. So that's only what they mean by a light inextensible string. The system is pulled up a rough plane. What does that mean?
There's friction.
There's friction, okay, at an incline of 30 degrees to the horizontal by means of a constant 40 Newton parallel to the plane. In other words, the 40 Newtons is not making an angle with the object, as shown in the diagram below. The magnitude of the kinetic frictional force between the surface of the 4 kilogram block is 10 Newtons. The coefficient of friction between the 1 kilogram block and the friction is 0.29. Okay, so we'll get to frictional force in just a minute, but let's just consider what is going to be the formula that I want to use in this system. Okay, let's look at the system as a whole first. Let's look at everything first. So imagine these two are actually just one block. Okay, can you see what I'm saying? In other words, we're just looking at this string right here. Let's just first look at that string there. Okay, the tension in that string must be equal. Okay, so the tension in this string is equal to the force applied. Okay. the tension in this string, so let's say that's T1 and that's T2, is also equal to the force applied, but it's equal to the force applied by so here, there's a guy pulling a string. There's a guy pulling this, okay, on that string. On this, on this box, it's not just a man pulling on the string, it's the man and the box pulling on the string. Okay, so just keep that in mind. So the whole story is a slightly a bit more. So it's the force applied by the man and the box together. Now, some of the force that's being applied, in other words, some of the weight, so the work being done by the applied force, is used up by the first box, and the rest is used by the back box.
Okay.
Does that make sense?
Yeah.
So some of the work done, so in other words, the force that's applied on the bottom box, even though I'm saying it's the man and the box that applies that force, it's actually less than the original force, because if I say man and box, it's actually minus what the box has used. Make sense? Okay, we'll look at it just now. Okay, let's think of the system as a whole first. If we know the system is of a whole first, if I wanted to find the force, well, I'll explain it as we go. As a whole, imagine this 1 and a 4 kilogram box was one box.
Okay.
Okay, so
With no T2.
Sorry?
Then
There's no GT.
Okay.
Yeah, so imagine they just connect
Cool.
together.
Alright.
Okay, what would be our formula, our cool generic formula?
Work net.
Yeah, work net is equal to
change in kinetic energy.
change in kinetic energy. And then, what would be net incomes? Or net income forces?
Well, gravity is against.
Again, so gravity is
Yeah.
going to be an expense.
So is frictional force.
So it's frictional force.
And force applied is plus, isn't it?
Yes, why?
Because I'm the one pulling
Pulling, and in which direction is the box moving? On the
upwards.
box. Yeah, so it says a block of mass 1 kilonewton from like that to a string. The system is pulled up a plane, so it's moving upwards.
Upwards.
Exactly, is equal to the change in kinetic energy. So just keep that in mind.
That is cool.
Okay. Now let's quickly see what are all the energies for the first system.
Okay.
Okay, so just this top system. So this is the net income on the whole system. Now let's just look at the net income on the top system is what? Okay, what are all the forces applied? What are all the income and expense forces on that? So that one is the same. It's the net work done equals to change in kinetic energy. Now what are the income energies for, did I say the top one? Yeah, the top
Yes.
one. What's the income energies for the top one?
Isn't it the same?
Almost, except for one difference. Okay, so yes, there's work done by the applied force.
And
Then there is
gravity.
work done by gravity.
And also frictional force.
Sorry, subtract. But now, is the work done by gravity on the first part the same as the work done by gravity there?
No, it's
No,
different.
because it's different masses, okay?
Yeah.
So that would be one thing that's different. Work done by friction, would it be the same as the work done by friction here?
No.
No,
No,
it's different.
okay. The work done, are those all the forces acting on that box? What other forces acting on it?
Tension.
Tension. This block is pulling backwards on that thing. So whatever extra energy this guy has put into the first block gets used by the back block. Okay, so in other words, the net work done on block 1, okay, minus the net work done on block 2. That will equal a change in kinetic energy. Does that make sense?
It does.
It does. Okay, so in other words, we just need to understand that block 2 is also, he also has net work done, and but I don't know this. I'm winging all of this, to be honest. But it makes sense to me.
It does.
It does make sense to me. Okay, so there's another energy here, and that is the work done by that tension. So if I can, and that will equal the change in kinetic energy for block. What block? Block 1.
Okay.
Do you see that?
Please repeat that.
Okay.
Sorry, I got sidetracked.
So no, that's fine. So this force here, that's the force in this row, tension, is also being applied to block 1.
True.
So if we just consider block 1, we have an applied force on block 1, we have gravity on block 1, we have frictional force on block 1, and we also have the tension in the rope on block 1, and that will change, that will be equal to the change in the kinetic energy of what?
Block 1.
Block 1.
Okay.
But block 1 and block 2 is connected to the same thing, so their change in kinetic energy will be the same. That makes sense, eh?
So a quick question.
Yeah.
For block 1, right?
Yeah.
The tension 2 is pulling it backwards, right?
For block 1, tension 2 is pulling it backwards, yeah?
So it's helping friction,
Yes.
isn't it?
Yes.
So shouldn't we add the 2 if it's helping each other?
It's helping what?
Is the friction, tension 2 is helping friction, right? To pull block 1 backwards.
Backwards.
Yes.
Which is, so why do you want to make it a positive? Because it's working with friction. It's working in favor of friction.
Yes. So
No, I think she's saying we must add friction in the,
like
in the
say
tension of the box too.
Yeah, that's why
WA minus and then brackets
Yeah.
WT plus WF.
Oh yeah, that's
Understand?
fine. So if you want to just do it like that,
Yeah, because they're helping each other. Am I right?
you
Please
could,
do
but
that.
no,
same
no,
thing.
From the gravity.
but it's perfect. You're not wrong. But if I multiply this in, what do I
Let's take
get?
a minus.
I get exactly that. So if you want to do it like that, if that's how you understand it, that's okay.
Okay, cool.
Because it's working against, it's like friction working against the object. Okay, so good. So this is block 1. Okay, now let's just actually go and see what do they ask in this question. That's important as well. State Newton's third law.
What is it about again?
Forces are equal. I know.
Force.
Is it the action reaction?
Yeah.
Oh, the something applied on object A is equal to the something applied on object.
Forces equal.
Can you?
The person who's pulling the box, they're exerting the same force.
No, Newton's third law has got nothing. Well, it does have something to do with this question, but it isn't necessarily got to do with when you state it in words. You're not stating it in terms of this.
Oh, the force applied on an object is equal to the force. It's something about opposite and equal something something.
Yes, for every yeah, for every force applied, there's an equal but opposite
Opposite,
force reacting against that. Okay, cool. It's not. You're going to study your theory hopefully. Well, just so that you know, every exam has 4 types of questions. We get level 1 questions, which is theory questions. Yeah, that's considered the easiest because you should know them. Okay, in your exam, 10% of, to be honest, I don't remember the weighting. Is it 20? 20% is theory. Is level 1. I can't remember, but it's not bad. Okay. The level 2. This is an example of a level 2. Level 2 is usually, and this can also be probably level 2, this might be level 3. Level 2 is like standard understanding. So it's basic, give the formula, substitute in the formula. They're usually between 2 and 3 marks for level 2 types of questions, but that makes up about 35% of your test. Okay, level 2 marks. So now we're already at 55%. 55% of your exam is literally things that you've been doing the whole time and your theory. You should get at least 55. Questions like that's usually 6+ are level 3 type questions. They are questions which usually you need to use more than one step to actually get to the answer. Okay, that's like that's typically like that slide we were looking at. What was that? This slide where you had to find the future velocity of this one to have the initial velocity of the next one so that you can find the future velocity in the end. Make sense? So those are level 3 type questions, more or less, and they're about 30% of your paper. Okay, and then you get level 4 type questions. Level 4 type questions are when we do the control test, when we work through that, we'll look at that. In terms of the exam, I did a video yesterday with the same formula with the students in Midrand, and I went through the exam with them.
So can I ask? Okay, I'll ask when you're done.
Yeah. Well, with the exam with them, so I'll put that video on. You guys can watch that video on the exam questions. Then I'll do the control test with you, and you guys can see, and they can watch the video. And the next week we'll do it opposite way around. We'll do the exam with you guys, and then the control test on chemistry. Okay, is that fair enough? But you're both going to have the same. Going to be able to watch the video, so. Okay, just so that we can cover more stuff. Okay, cool. Level 4 questions is then questions that require insight. If you think of the control test, there was one question right at the end that was asking something, or a question like that guy that was diving into the water, explain what he could have done in order to avoid injury. Okay, and then use physical science reasoning behind your question. So it's insight questions, it's advanced questions, and that's only about 15%. Okay, so obviously level 3 and 4 questions are more difficult, but everyone can and should get at least 55 because it's literally just doing what you've been doing in class. Okay, cool. Let's then go and look at their questions. This is a level 1 type question because it's just recalling a fact. Draw a labeled free body diagram showing all the forces acting on box 1. So let's draw box 1. Free body diagram. Free body diagram is actually an object. Okay, here's my box 1. What forces are acting on it? Let me put just my surface in, but you're not allowed to draw in the surface when you do your diagrams, okay? So do it in pencil and wipe it out afterwards, okay? That is important. You said gravity, okay? So gravity, in which direction is gravity?
Downwards.
Always down. Okay, what else?
Force applied.
Force applied, in this case is?
Upwards.
Straight up.
No. That way.
Up the incline.
Yeah.
Okay.
And then
right.
frictional force, the opposites.
Frictional force will always be opposite. Look at that.
And then
I mean, we
what is
already
it? Normal force also.
Yeah, perpendicular to the surface.
This one, guys, I don't know why everyone put normal force and weight always in opposite directions. Normal force only applies when an object is on a surface, and it's always perpendicular to the surface. So it has nothing to do with weight. Well, it does have something to do with weight. Its value, the size of normal force, depends on the weight of the object. Okay, because the heavier the object, the normal force is the force that the surface applies to the object. So the heavier the force the object is, the more the normal force must be. You see, that's the only difference. Okay, what is the normal forces of an object that is vertical?
0.
0, because of course the surface isn't doing anything anymore. You understand? So an object that if an object is moving up or down, there's no normal force. So there's normal force. Very few people actually got this in the exam correct. Normal force. Okay, this is weight, not G, not gravity. Gravity is not a force. Okay, weight is the force. Friction, you can put lowercase f. Applied force, you can either say F, A, or T for tension. Is that all the forces acting on block
And tension.
What tension?
Don't you have tension? Because
Kinetic tension.
Kinetic friction.
No, kinetic.
We've already done kinetic
Love
friction.
it.
Friction is already there.
tension.
What tension? It's 5 months, so you can be sure there's another force there. So look at the object. What forces are acting on it? Well, there's a guy pulling on it up there. There's weight pulling it down there. There's normal force up there. There's frictional force down here. What else?
There's also tension.
Yeah.
Why? From where?
From the bog.
From the bottom box. Well
Yes.
done. Bottom box. You see it's tension, and I ask you what tension.
It's like you like what tension?
I don't mean. If I ask you a question, I don't mean you're wrong.
Explain.
I just need an explanation. Okay, yes, there's tension from block 4, from the 4 kilogram block. Okay, makes sense?
Yeah.
Okay, excellent. So, if we look at this, you'll see here we have all of those forces in our formula except for the normal force, because the normal force cannot do work. The reason why a normal force cannot do work is because a normal force is perpendicular to the surface, and a force can only do work if you move in that direction. Now if I put something on the table, normal force is not moving it, it's stopping it from being moved. If I put something on here, normal force is not moving it in that direction, it's stopping it from moving in that direction. Okay, or from moving in that direction. Okay, so normal force is the only one not in there, but look there. There's the force applied, there's the gravitational force, there's the force of friction, and there's the tension in that row. And normal force would just, you can do normal force, but remember the work done by the normal work done by any force is the work done, normal force, the change in that times cos of theta, which is the angle between the displacement and the force, which is 90 degrees. What is cos of 90 degrees? 0. So that's why the work done by the normal force is 0. So you could have put work done by normal force in there. So I love this. This is going to work. I'm so excited. Okay. Excellent. So let's look at the next question. Tension. Calculate the magnitude of, and just so that you know, this question, what level question do you think that is?
The drawing labeled what?
That's level 1, so we've got honors. I think.
It's level 2. It's level 2 questions because it's really just standard. It's a standard. So level 1 is knowledge. In other words, you just recall. You just like, what is the definition of that? What is the momentum conservation principle? What is level 2 question is doing things, is like actually doing something based on what you have been doing in the class. Make sense? Yes. So that definitely level 2 question. And then this one, calculate the magnitude of the kinetic frictional force between the 1 kilogram block and the surface.
F is equal to coefficient of
F coefficient is equal to coefficient of friction times
times the force times the force.
Normal force. Guys, this formula is not on your formula sheet. You have to know it. Okay? I don't think it's on your formula sheet. I've never seen a formula sheet with it on. Okay? You have to know it.
I don't see it.
There's no forces.
This is the wrong page though. There's another page. Okay. But how do we calculate the normal force? Okay, let's just quickly look at how should we calculate the normal force. So here we have our surface. The normal force is perpendicular to the surface. And the point of the normal force is that if I take the weight and I move this vector there to that top the vector will touch my surface. So the normal force, so obviously all I do to find the length of the normal force is I move my vector. So I have my surface, I take my weight, and I take this and I just move it up. So just this vector and I move it up. Oi. The same distance, I move it up. And then all I do is I take this top and I connect it with a 90-degree angle there. Okay? Then this would be the length of my normal force. Now, that's like, oh, that's cool to draw, but how do I calculate it? Okay? Cool. Here's the point. That is theta. This is 90 degrees. That is 90 degrees, and that is theta. So this angle and that angle will be equal.
Okay.
Okay?
Yes.
So if I know this angle is equal, I know what weight is. How do I calculate weight?
In distance.
Mass times gravity. I can get weight. Now, can you see the triangle? The normal force is what? Opposite, hypotenuse, or adjacent?
Adjacent.
Adjacent. Can you see that it's adjacent? The weight is what? Opposite, hypotenuse, or adjacent?
Hypotenuse.
It's the hypotenuse. In other words, I've got the weight and I've got the hypotenuse and the adjacent. So I'm going to use which trig function?
You have the adjacent and
The weight.
the
Sorry, adjacent and hypotenuse. I've got the adjacent and hypotenuse. Which one is adjacent and hypotenuse?
cos.
Cos. So in other words, cos of theta is adjacent, which is normal force divided by hypotenuse, which is weight. So the normal force is weight cos theta. So in other words, if you want to, you can rather, I mean, if you have to remember that formula, might as well just remember this formula instead. Isn't it? It will always be that formula. And where theta is the angle. So if theta is 0, if the angle is horizontal, cos of 0 is 1, then it would be just coefficient of friction times weight. Make sense?
Yes.
Cool. So here's our formula to use. We have our coefficient is the 1 kilogram block has a coefficient of 0.29. 0.29. Weight is mass of the 1 kilogram block, which is 1, times gravity, which is 9.8, times cos of 30 degrees. Because that's the angle. What do you get? We just do it with me so that we get the answer verified.
Okay.
I'm going to intrude a pen. Girls out there.
Do you get the same answer?
Yes.
2.46. Excellent. Cool. Now they ask me to calculate the tension in that string. And now, I think probably all the students I know will just say, yeah, right, let's go on. Okay.
Yeah.
But why? Because you have this lovely formula where you can say that tension is in this formula. So look at how cool this formula is going to work out. We've got our work done by applied force is force of applied times delta x. Okay, minus the work done by gravity is mass times gravity times delta h. Do we have delta h? Do we know how high this thing is? No. So let's use that other one. Instead of saying delta, we'll say delta x sine of theta. Okay? Minus the work done by friction. Okay? We look at this. The work done by friction is what we just calculated here. It's that frictional force. And remember, we did this formula for the work done on this box. Okay? So minus the work done by friction is that times delta x. And then we have the work done by the tension is the tension force times delta x is equal to the change in kinetic energy. So let's just go and see, what do they say about the change in kinetic energy? They don't say anything, so let's just keep it for now. Half mass times, and then I'm going to put it like this: future velocity squared minus initial velocity squared. Okay. Now I just want to show you something. Okay. In this formula, we have absolutely everything, except for what? Do we have the force applied?
Yes.
Do we have delta x? In other words, the distance from that it's been moved over.
They didn't say.
They didn't say, but that's okay. Just keep that in mind for a little bit. So we don't have that. Do we have the mass? And again, I'm talking about the block. It's the first block. We have mass. Yes. We have gravity. Yes. We don't have delta x. Okay, so let's put delta x in a red. We don't have it. We don't have it. We've got the angle, isn't it? Do we have the frictional force on the first block? Yes. Do we have the delta x? No. We don't have delta x. Do we have t?
We're looking for t.
No, I don't have t. Do we have delta x? No, I don't have delta x. Do we have the future velocity and the initial velocity? Let's go back. As pulled the anchor to the horizontal by means of constant diagram, the magnitude of kinetic force between the surface and the block. Between the surface and the block. No, we don't have any one of those two. Do we? Did they say anything about? No, they didn't say it. Okay? So we don't have that. Now, what I just want to show you here is, since we don't have these two, let's try that other formula. Okay? Remember we said net work done is equal to the change in kinetic energy. Okay? What is net work? It is the profit, but you can also say it's the net force times delta x.
Okay.
Isn't it? Because that's what the formula for work is: take the force and multiply it with the displacement. So instead of writing this, let's rather than write net force times delta x. Let me quickly show you why. Because now all of a sudden I've got delta x in every single term.
You can just divide it away.
I can just divide it away. Awesome. So now I've got force applied minus mass times gravity times sine of theta. I've got all of these values minus F minus T minus the net, minus is equal to the net force. Okay? And that's the net force acting on object 1. Okay? Now, do I have the net force acting on that object? I don't see a net force acting on the object, the magnitude of the kinetic, but they have to tell us they don't tell us anyway that it's accelerating, is it?
But sir, oh wait,
No,
no,
they
it's not.
don't.
They don't say it's accelerating, they don't say it's a constant velocity, but they have to tell us that. So I must be honest, I think there's something missing in this question, because we have to know if it is accelerating or not. We have to know if kinetic energy changes. So I'm assuming, maybe it says, just let me just go back
It's
to the
not
question.
good to assume.
No, but if they don't tell me, I know I 100% agree with you, you're never allowed to assume. But they don't tell us anything on whether this. So they say a block of mass is connected to another block by a light, and the system is pulled up a rough incline to the horizontal by means of to the plane in the diagram shown below. The magnitude of the frictional force is the surface is that.
Only one is just change.
No, they don't tell us anything as it moves up the incline. So, to be honest, I don't know what you can do other than just assuming that it's going at a constant, in which case, instead, if I knew, sorry, I thought they would tell us about something about, but okay, let's say that's the case. From the beginning, from here, we could have then said, if it says constant velocity, we could have just said that is 0. And if that is 0, then this would be 0. I could still divide away delta x, because on this side, 0 divided by delta x is still 0. So I could have still divided it away. But okay, let's say it wasn't the case, and let's say we now had mass times acceleration. Sorry, we had net force here. Then I would change it to mass times acceleration, because net force is equal to mass times acceleration, but now acceleration is 0 because it's going up at a constant velocity. They don't tell me that, but they're saying it's being pulled up. They're not giving me anything regarding the velocity. Is it going from so nothing. They have to tell me something, because it's part of how you get the net force. So I must be honest, I think there's a mistake. So let's then assume it's at a constant velocity, which means this is 0, so that I have my formula: force applied is mass times gravity times sine theta minus the frictional force minus tension, and then tension would equal this. Force applied, which is 40 newtons, minus mass, which is 1 kilogram times 9.8, 1 times 9.8 times sine of 30 degrees, minus the frictional force on the first block, which we worked out in the proof.
2.46.
2.46, and that's it. Just calculate.
Sorry, is that tension as in T2?
Yeah.
Won't it have to do with the difference between the forces of the 4 kg block and
We get-
that one?
What did you get?
Because we haven't calculated.
What did he get?
4 kg block.
Same as
Let me
32
just
comma?
quickly get this
same as
answer.
How come?
What if they don't?
6 or that?
6387 something.
6877.
Thing is, I can't operate this one here.
I got 32,64.
0.64.
Yeah.
Okay, so let's look at it like this. Let's say if we calculate it using this formula, that the net work done is equal to mass times acceleration, then we can get the net work by, or we can get acceleration by taking the net forces acting on the whole system divided by the mass of the whole system. So we're now considering this one as a unit, just to work out at what acceleration is it going up. I made the mistake, you were correct. I'm not allowed to assume it's going up at a constant velocity.
Yeah.
Okay, I'm supposed to go and calculate acceleration using net force. Now, so let's do that. So if we do that, then the net forces acting on the whole system is the income forces minus the expensive forces. So our income forces is force applied, our expensive forces is frictional forces, and our weight is the weight in the direction of the weight perpendicular to the surface. That's all the forces acting.
Sorry for interrupting you, but why consider it as a unit when those factors are not the same?
Because assume just for a moment that they weren't connected with it. Let's shorten that string. And so they didn't tell me how long that string is. Okay?
Yes, but they did tell you the force on the string.
This string?
Yes.
No, they haven't.
The part where it says the magnitude of the blah 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 4 kg block is 10 newtons.
That's this force. That's frictional force. We're actually trying to get the tension in the string. We're trying to get T2. For 6 marks, they didn't give it to you.
Okay, but still, I don't understand why we're considering it as a unit.
Okay, because this guy is pulling it up the incline with a certain, he's applying a force.
Yes.
We want to know, is that force enough to let it start accelerating up? So let's just for a moment consider the whole unit, all of the energies that's being, so I mean we could use...
So tension doesn't play a role now?
Not yet, because we're looking at the whole system, because the whole system is moving up at the same acceleration. Would you agree with that?
Okay, yes.
So in other words, the acceleration applies, if I'm trying to get the acceleration, it applies to the whole system.
I'm trying
Okay,
to...
let me give you the formula. Formula for tension is my mass times acceleration minus weight. Okay. Now, so I'm trying to get tension, acceleration.
Yes.
I've got weight. It's weight sine theta because it's on an incline.
Yes.
This is, if I'm talking about tension in rope T2, it is this. It's this thing's weight. That thing's weight has nothing to do with the tension in T2. Does that make sense? Okay. So
mass is 4 kg, then we'll use the 4 kg mass.
yes, this will be the 4 kg mass. Okay. So this part will only apply to that part of the block. Does that make sense?
Okay.
But the mass times the acceleration, the mass again only applies to this part of the block. But the acceleration, yes, it applies to this part of the block, but the acceleration, both of them are accelerating at the same velocity, the same acceleration, because they're connected with that string that is inextensible. So in other words, if I can find the acceleration of the whole system, I can find this value that I must use in there.
That's what I was trying to say.
Yeah. I like that look there. Then once it goes, oh, then we'll never forget it. Okay, so just tell me, what is your objection at this point?
Okay, I don't understand why we are ignoring the factors of the 1 kg now.
We're not gonna. We're gonna take it into consideration just because we're going to, when we consider the system as a whole, we're including 1 and 4's factors.
But if
So
we
we're
want,
back to what you said, they gave nothing for no reason.
so if we want tension, isn't it T1 and T2?
Okay, so T1's tension, let's see, T1's tension will equal the mass of which object? T1 is pulling which object?
Both.
Both.
Okay.
So it would be the mass of both. Mass of 1 and 2. Acceleration would be acceleration of 1 and 2. The weight would be the weight of 1 and 2. Because rope 2 pulls on both. Rope 1 pulls on both. Rope 2 only pulls on
the 4 kg.
on the 4 kg. It's connected to the first one, but that first one is pulling. Does that make sense? You sure? Okay. So this is the acceleration of 1, but the acceleration of 1 is equal to the acceleration of 1 and 2 together.
Okay.
Do you understand? So in this formula, we have everything, but we don't have the acceleration of 1 and 2. Okay, so we want to go and calculate the acceleration of 1 and 2. Now,
We have acceleration for 1.
we don't. We don't have the acceleration. We must go and work that out. And the way that we will work that out is with this formula. You can use my formula. It's sad it didn't work. But I'll have to figure it out. So what are all the forces acting on the system as a whole? So I'm considering acceleration of 1. I can go and work out what's the acceleration on object 1, the first block. And then I just look at all the forces acting on the force block, because I want to get net force. And I want to divide by mass. So if I try and look just at object 1 to find its acceleration, one of the forces is an unknown force.
But you're saying we're ignoring tension because we're pretending.
Yes, yes, we're pretending that it's 1, but I can pretend that it's 1, or I can pretend that it's 1, or I can just look at 1, or I can just look at number 2, because the acceleration, this one's acceleration is equals to that one's acceleration is together equal to the total, if this is 2, then that is 2, then the whole thing is 2. Does that make sense? So I can go and look at what are the net forces on this one. So I can say if net forces on object 1 is equal to the acceleration of object 1 divided by the mass of object 1, but the net forces on object 1 includes tension, which I don't know. So then I can say, okay, well, let's then look at the net forces on object 2. On object 2, there's weight, there's friction, there's normal force, and there's tension. So for object 2, I can also not use. So then I say, okay, well, since tension is the problem, it's the unknown, let's look at the whole system together as one. And so then I'll look at F net of the total system, and then I'll just look at the acceleration of the total system divided by the mass of the total system. Does that make sense? So in other words, since this total acceleration for all of it is the same as the single accelerations, I can then use it to find the rest. So in other words, that's what I'm trying to calculate. I have the force applied, so I'm looking at the total system. I'm looking at the whole thing as one unit, as if it's one block. And then I see, well, if it's one block, then the force that I'm applying is 40 newtons. The friction, there's now two frictions I need to consider, the one that I calculated here and the 10 newton associated with the 4 kg block. So there's a, sorry, I'm going quick now, 2,46 minus the 10 kgs as well. And then there's the weight of the whole system, which is 5 kilograms.
Minus the 10 kg.
Wait then.
10 newtons.
Oh, I thought you said 10 kg.
I probably did. I'm sorry. 10 newtons is the kinetic friction between the 4 kilogram block.
Oh, okay.
Okay, minus sine, and then it's 30 degrees. Is it? Was it 30 degrees?
It's
30 degrees.
Yeah.
That's the weight in the direction. So remember, we'll always have to, if it's on a surface, we'll always have to do weight as a sine of 30. Okay, divided by the mass of the whole system, this will give me my acceleration. So what do we get? 40 minus 2.46 minus 10 minus 5 times 30 sine 25.04. Oh, I must still divide with 5, thank goodness. Because to accelerate at 25.04 meters per second, that guy is running up Usain Bolt speed up to 5,008 meters per second square. Okay, I'm not allowed to round off till my final answer. So now, remember what I said here. We could have used this formula instead. We could have found acceleration by saying that the acceleration is the same for block 1 or block 2. So I could have said acceleration is the net forces on block 2 divided by the mass of block 2. Now look just why I'm going to do this, because the net forces on block 2 include that tension. So let's say the net forces on block 2 is the income forces. The only income force is the tension that's pulling it up the incline, minus the frictional force on it, minus the weight of it in the direction of the surface, divided by the mass of the block.
Okay.
With me? Okay. Which means that I already calculated this now as 5,008 is equal to the tension is what I'm trying to find, minus the friction on that block was 10, minus the weight of that block is 4 sine 30 divided by 4. So I multiply 4 on both sides is 20,032 is equal to 10 minus 10 minus 2 is 12, so T is equal to 8,032 newtons. It's not the same answer I got before.
8?
How did you get 8?
It's 5.088 times 4. And the sum of that is minus 2.
Where did I get 8?
But 10 is the other side.
20 minus 10 minus 2.
You're supposed
Wait,
to
it adds up. It adds up. Sorry. So that's 32.0. What was my answer?
32.64.
It's 32.0.
What is it now?
32.
Shucks, but that's closer. Come.
It is.
It's
but it's by
probably
luck.
wrong.
You know,
it's luck, you say.
Yeah, it's by luck. Because you didn't consider totally the 4 kg block on this one. That's why.
I don't know. Oh yes, I didn't consider acceleration as well. I said it when it constant.
Yeah, you said the acceleration is 0, you understand?
Yeah, I see.
It's by luck, yeah.
It's by luck. Oh, that sucks. Okay, I'll still figure it out, I'll tell you that. Okay, I want to use that formula for everything. Okay.
Yeah, but it's a nice
I wish I knew it before I got married, I would use it to propose. Okay, so let's quickly look at... Sorry? No, that's yours.
Is it?
Yeah. Yours.
that
They
looks
just
proper.
don't have a file because we only give files to people whose files are going to moderation.
Okay.
So we have to have files for them. So yours is going for moderation.
Okay.
Your tests are in there. Did you get
This
yours?
is nice.
Wow.
Yeah.
Hey.
But you don't get to keep it.
It's okay.
It's in your life.
Okay, so
And
let's
it's my
quickly look at the... Okay, let's look at those control test questions. High diving is the act or event of diving from extreme heights. The current world record is held by Rudolf Bock from the Czech Republic. He dived from the Zakov Bridge, a steel arch that spans the Volta Tower. Tava River. The height above the water at the time of his dive was 58,28 meters. Explain the term free fall. What is the term free fall?
When an object is
Falling.
when it's falling with no, I don't know, like there are no forces acting on it besides gravity.
That's it. That's it.
Yes, that's
It's when the only force acting on an
Yeah.
object is the force of gravity. Excellent.
Yeah.
Assuming that Rudolph just fell from the bridge, in other words, he did not jump, calculate the velocity wherewith he will hit the water. Okay, again, I'm gonna now use my phone. Okay. So the velocity wherewith the reason why I want to use the formula is to show you can always use it. Okay, so if an object is just falling from a bridge, he's now a person, but he's just falling from a bridge, what are the income and the expense energies that's in the system? So we know the net work done is equal to change in kinetic energy. So what is the net energies?
Gravity.
is income.
Gravity's income, because he's okay. So we only have that's what we said in the previous.
Yeah.
It's only gravity acting on it. So there's only gravity, and that will change his kinetic energy, which is half mass times future velocity squared minus a half mass times initial velocity squared. And also we know that the work done by gravity is mass times gravity times its change in height. This is now typically an example where mass times gravity, the change in height, we don't need to use delta x sine of theta. You could, but remember theta is the angle I make with the horizontal. Now he's falling like this, so the angle is 90 degrees. Sine of theta, sine of 90 degrees is 1. So you could use this formula, or you could just, we're only considering height anyway, it's not really left or right. So we could just take the work done by gravity as mass times gravity times height.
So
Yes.
the formula you just used, isn't that kind of like also the EP formula?
That's exactly the ED formula. That is potential energy. Potential energy is the work done by gravity.
Oh, okay.
Make sense?
Yes.
Cool. So half mass. Now notice here also mass velocity squared future minus mass is in every term.
Cancel.
So I can cancel it. Okay, I don't need to use mass. Okay. Also notice that they say he fell from the bridge, which means initial velocity is zero. So this term is in any way not even being used. And so we have 9,8. The height was 52,28, I think.
Yes.
Meters. Let's leave it out. Is equal to a half the future velocity is what I'm trying to calculate. And so I just multiply both sides with a 2. So future velocity is the square root, because it's square, plus minus really, of 2 times 9,8 times 52,28. What answer do you get, Bukani?
It's 32.01.
Meters per second. Apparently I'm not allowed to write like that. So. Meters per second. Cool?
Yes.
That's fair enough, okay? Draw a vector diagram of all the forces acting on Rudolph the moment he hits the water. So now, the moment he hits the water, what forces are acting on him?
Still gravity.
Gravity is still acting on him. And? Will he still continue to fall at the same velocity the whole time as if he's been falling through air?
No.
Why not?
Because it's a different medium.
It's a different medium.
Yes.
But why does that make a difference? What do we have to consider now? is he going to slow down?
Yes.
Which means there is a force in which direction? Does it make sense?
Yes.
If it's going to slow him down, there must be a force slowing him down.
But what is that force?
Well, it's in the opposite direction. When you
Frictional force.
Oh,
Is it?
the friction caused by the water.
But, sir,
Isn't
what
it
is frictionless?
Impulse. What is impulse?
Impulse is the change in momentum.
Oh yeah, sorry.
So frictional force is when he makes a splash, like.
No, the splash comes from the collision, because now he is the same as the force. There's a force acting on him. He's acting on the water, and because he's acting on the water splashes. Okay, so that makes sense. That's why it splashes. But the question is, why is he slowing down? Because there's a force in the opposite direction. Now, specifically water and air, we call it drag. It's drag force. It's what we call the force caused by an object going through any medium. Is it experience a drag force, which is the force of the medium that you are traveling in. Okay? You didn't have to know that. I gave you...
I know drag for the air, but also in the water.
Also in water, it's called drag. Even later on, there's another question where it talks about the boat going through the water, and then I used again the word drag force, the friction experienced in water. So I even gave that word later on in the test. But come on, you guys are confused. Why?
Because water, like everything just changes, hey?
How is there friction in water? Like,
Really?
water is, like, it's frictionless.
Have you ever jumped from a high height into water?
Sir, but no, sir, it doesn't
Did you know
make
you
sense.
can die falling on water? No, really. There's people who die falling on water because you are changing from the air friction all of a sudden to a different friction, which means that that friction now works against your motion. If that change in momentum, remember what the formula is: net force is equal to change in momentum over time, change in time. So if you now fall on water, the velocity changes so quickly that the force that you are experiencing is so high it can kill you. Would you say there's friction going through mud?
Yes.
Have you ever tried running in water?
Yeah, it's kind of difficult.
It's difficult. Why? What makes it difficult?
Okay, maybe.
It would be easier to run on the moon if the moon had better gravity than to run on Earth, because there's no air. Air still has friction. Why when you run does your hair blow? It's friction that causes your hair to be affected but your body not. Well, not as much. It is affected. The faster you go, the more it will affect you. The reason why in motorbikes, the maximum land speed for motorbikes is limited at about 400 kilometers per hour. Because the moment when it gets near there, people can't hold on anymore. Why not? Air friction. Does that make sense? So in the same way, just as air, water has higher friction than air. Water doesn't have friction because it's no, there is friction in any substance that you travel in, any substance, and it's called drag. Okay, so there's friction on a surface. That is just surface friction. That is difficult to push something if it's on a rough surface because the surface is resisting me. But just like if you think about in chemistry, we call it viscosity. Resistance to flow. The higher viscosity is, the more difficult it is to flow, which means the more it resists something to go through it. Okay, so for example, syrup. If you were to try and drop a ball in syrup, it would blip and then slowly go down, while in water it will go faster. Why? Because the resistance of the resistance caused by syrup is higher than the resistance caused by water. If alcohol is even a less resistance, so if we dropped it in alcohol, water, and syrup, alcohol will go down first, then water, and then syrup. Okay?
Okay.
Makes sense? So, is there friction in water?
Yes.
There's friction. Only place where there's not friction is actually in space. There is a little bit of friction in space, but in a vacuum, when there's nothing. That's the only time there's no friction. Usually we say ignore air resistance, air friction or air resistance, whatever they say. Anyway, yeah, let's go back. So there's two forces. There's his weight and there's frictional force or drag. If it says two, there's two forces. You can know that. The marks. If Rudolf had a mass of 74 kilograms and dived 15 meters deep into the water, calculate the average force applied by the water. So there's a force applied by the water. What force would that be?
Frictional force.
Frictional force. The force applied by the water would be the frictional force of the water. But if you called it force applied, that's okay. I didn't expect you to know friction, but know that the water is applying a force on him. From the moment he entered the water until he reached this depth, K, let's use that formula. Okay, so I'll just change the color again a bit. Okay, so let's go. Net work done is equal to a change in kinetic energy. The net work done, what would be income so now we're in the water. Did something change? So remember he's now falling from the top. There's A, point B, he hits the water, and then there's point C. So is this the initial velocity if I'm working while he's in the water? No. Can I use that initial velocity? No, this is two stories. I must use the final velocity here as the initial velocity for BC. That makes sense, doesn't it? Okay, so we're working on BC. While in BC, we've got these forces acting on him. And what are the income forces? What are the expense forces? Sorry, the income energies, expense energies. There's only two forces, so it can only be two. So it's traveling down, remember?
So gravity is the income.
Gravity is an income.
And then frictional force is the expense.
So the force applied, and they ask us to calculate the average force applied by the water. Okay, so this is the force applied by the water, or whatever you're going to name it. It doesn't matter what you name it. You just know that force is stealing energy. Okay. Is equal to the change in kinetic energy, which is a half mass future velocity squared minus a half mass initial velocity squared. Okay, what is the mass? The energy done by gravity, the work done by gravity is mass times gravity times delta H. So what does delta H represent in this case? Is it the height of the bridge?
No.
What is it?
Deep into, so it's the water.
It's the depth. He dived 15 meters deep. Okay? How would we calculate the work done by the force applied by the water? So let's call it frictional force, just so that we have something. The frictional force of water
delta X
times delta X. In this case, delta H and delta X is equal.
Okay.
Do you understand why? Does everyone understand why? Okay, it's equal to half mass. We know mass. What would the future velocity be? Where's the future velocity in this story?
Beginning B. Future is C. Initial is B. Okay.
Cool. So we have the future velocity is. What did you say is the future velocity? Where's future velocity? B or C?
C.
At C. What is his velocity at C?
His final is 0.
Is 0. Why?
Well, that's what the final destination is.
If it wasn't 0, he would still be going down, isn't it?
Yes.
It's 0 because he's diving and he's slowing down and reaches 0, and now it's probably going to go up because of buoyancy, because the water is, yeah, he will start swimming up. Okay, so it doesn't matter. So, in other words, the final velocity would be 0, so this term is going to fall away. Does that make sense? So it's equal to minus a half mass times initial velocity. What's the initial velocity? Where will we get that?
From that question, which is that one.
The previous question,
Yeah.
at 32. Excellent. So here we go, and we need to work out frictional force. And so I just put in my mass. They said is 74. Gravity is 9.8. Change in height, he died 15 meters. Minus the frictional force is what I'm trying to calculate. The dive is 15 meters, is equal to negative a half. Mass is 74. And velocity is 32, actually, it's velocity squared. And in the previous question we had velocities. Oh no. 32,01 squared. Okay, so we get negative F15 is equal to negative 1,274, 32,01 minus 74, 9,8 times 15. Okay, so F is equal to that answer. What do you get there?
It's 3,252.64.
Is that what you get for this part? Or have you already divided with the 15?
Already divided.
So it's 3,000?
It's 3,252.6.
272.
No, 252.
52.
252.
Yeah.
Comma?
6.
5.
What's the last
5 Newton.
15.
Nonsense, heavy force.
We're getting something different.
Is it?
Let me
Okay.
see what you did.
So we have 74 times 32.
How would we do
Point.
it if I get a number like this?
01 divided by
It
2
can be like
minus 74 times. I shouldn't be minusing, I should be adding.
yeah, some big numbers. Some
9.8 times 15
2014.
is equal to that divided by 15. Whoa! Doubt that's correct. Okay.
Yes,
And,
you
oh, I
wanted
forgot to
to-
square this. Okay, so 32.01 squared times 74 divided by 2 is that. It's a massive number. Okay, plus
No, there's
74 times 9.8 times 15. Is that divided by 15? You're right. 325,265. Yeah. But that would make sense now for the next question down here. Rudolph sustained serious injuries, multiple fractures to his thoracic vertebra in this, and you can see why. That's a massive force that applied to him. I don't know how deep he
The
died.
market location is crazy though, because
Was
you
7.
think, yeah, you think like there's a lot that goes into it.
It is a lot that goes into it. It's just my formula that's not cool.
Yes, yeah.
So you get
What
a
is the distance of AB?
AB,
Yes.
52 meters.
Oh yeah, that's one.
That's far, yeah. Okay, so yeah. So for example, this. There you get a mark. 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 And
That's a cool formula, hey?
yeah. Oh, and you get a mark for that one. That's 0.
When did you
get a
figure it
mark.
out?
The formula.
Yeah.
It follows directly from this, and it's just the way that I understand it. And I figured it out last month. The formula I use is work applied is work in the course, I use this formula. Work applied goes into work done by friction plus work done by gravity minus the change in kinetic energy, or plus change in kinetic energy, and it's the same formula.
Yeah.
If you just take all of this to the one side, so all I'm doing now is I'm just rather explaining this rather than giving you a fixed formula with negatives and positives and whatever. So yeah, it seems to work. Let's just quickly draw a rough acceleration versus time graph. Okay, no values needed. So here's acceleration versus time. Initially, what is the acceleration? Because remember, there's now two parts to this question. There's acceleration here and there's acceleration there. So for point AB, so let's say this is time A, this is time B, that's time C. What is the acceleration initially?
It's probably higher than BC.
No, he's falling. What's the acceleration when you're falling?
So the initial
Huh?
Isn't it?
0? I don't know.
Like it's gonna go
Initially, gravity.
Oh.
Can you look, please?
Aren't you falling faster and faster and faster and faster? Why are you falling faster and faster and faster and faster? Gravity. 9,8. Okay? When you're falling in the air, your acceleration is 9.8 fixed.
Yes.
Always. As you're falling. Unless you open a parachute or you fall into water or something
Physics can get
happens.
so complicated.
But it's really not.
Oh.
Come on. No.
You just,
How
I
simple
mean, if
is
they
that?
mention,
you just said
I'm
gravity.
saying if they mention that he has a parachute, I'm saying physics can get complicated.
Oh, it can get, yeah.
So
but
please
then,
don't tell me. Gosh.
so, no, that's a great question. I'm going to put parachutes in my next question. But but think how simple it is. The moment he opens the parachute, it's like he's going into water. Why is he not? Why is he slowing down when he opens a parachute?
Yeah.
What causes him to slow down? What force is now acting on him?
It's more big to make
Friction. Because it's working against his motion. Make sense? Or you can call it the force applied by the parachute. It doesn't matter what you call it. But it's just in the opposite direction. That's what causes him to fall slower. Makes sense, huh? Okay, so in this case, in B to C, we don't need to know what the acceleration is. They said no values needed. But what can you tell me about the acceleration between B and C compared to the acceleration of VB? Again, acceleration is always constant. In high school at least, we always only use a horizontal line for acceleration. So what would the acceleration graph look like? Or what can you tell me is the acceleration between point BC compared to point AB?
It's
It's
low.
negative.
What? You said
It's negative.
it's negative. Why?
When you look at the sketch, it's up, it's below the x-axis. That's how I understand.
No, that's fine. It is true. It is less. It's actually something that's something like there. Okay? It is negative, but why is it negative? Like, how were you supposed to know it's all of a sudden negative?
I used to describe it using this y and x sketch.
Sorry?
I used to describe it using this y and x sketch.
The y and x sketch.
Yeah, this sketch.
Which sketch?
Like Cartesian planes.
Like?
These y axis and x axis.
Yeah.
What do you call that sketch?
Oh, so that's why you're saying it's negative here, because if this was the y-axis, this would be negative.
Yeah.
I'm asking, why is acceleration negative? Like, yes, it's negative and
slowing down.
because it's slowing down. He started with no velocity, 0 velocity, and he hit the water with 30 whatever. So he was accelerating, he was increasing his velocity. So So acceleration is positive. From here, he starts with velocity and he ends with 0 velocity, so his acceleration is negative. He's losing velocity, so acceleration is negative. So that's you've got to mark for making lines horizontal, and you've got to mark for having 2 lines on either side of the sketch. Okay, the next question. Give one recommendation that you can make with an explanation from a physics perspective to reduce the risk of injury for high divers. Okay, so let's just quickly look at this at this formula here. If I change this formula, what causes the injury? What is the result? Why is he getting hurt?
It's because
Too much
of
force.
Whose force?
of the friction.
Frictional force. It's the water's force acting against him. He's acting on the water, and the water is acting on him. So let's just quickly, I just want to solve this quickly. I'm trying to get this value on its own. And so on the other side, I now have a negative mass velocity squared divided by, subtracting this one, mass times gravity times delta H, and I'm dividing with negative delta X, So I just want to get rid of the negatives, so there's a half mass times velocity squared, initial velocity, minus mass times gravity, plus, because I'm dividing everything with a negative, because there's a negative at the bottom, okay, plus H divided by delta X. So look now in this formula. If it's at the top, it means friction is directly related to anything at the top. If it's at the bottom, then the frictional force is inversely related. What directly related means is if I increase that, the force will increase. If I decrease that, the force will also decrease. And that's all I need to know. All I need to do is see, and remember delta X is the height, so I can just make this delta H as well. Okay? So what could I do to reduce the risk? What can I do in this formula to decrease the force that I'm going to experience?
Decrease the velocity, height, and
if I decrease my initial velocity, remember this initial velocity is not the velocity I jumped with. It's the velocity I land on the water with. It's the initial velocity when I enter the water. How can I decrease the velocity that I hit the water with?
You can decrease the mass.
Yeah?
The mass.
I say the height.
The height.
the height.
Okay. Obviously, if I decrease the height, I'm not going to be so hurt by the water. But then again, that is opposite what they're trying to do. They are trying to go deep. What is so decreasing? So imagine now I can't decrease the height, but it's a valid answer. I would have marked it correct. Don't jump from so high.
Yeah.
Just don't jump. But obviously you can't break records if you don't go higher. So it's not a good answer, but it's an acceptable answer. Okay. So that's the only way you can decrease the velocity you're going to hit the water with is by not going so high. Doesn't matter what you do. You're going to from that height you're going to hit the water at that velocity, no matter what you do. So velocity basically can only increase the higher you go. You can't decrease the height. Okay, so in terms of that, you could decrease the velocity. What else can you say?
What are we decreasing here? The force.
We're trying to decrease. This is the force that water is having on him.
So we are trying to decrease that.
Yes, because if we can decrease the force, we can decrease the injuries that you can sustain.
But if according to this, if you decrease the height, which is inversely...
No, what height is this?
No, I'm talking about the height...
Doesn't matter which one, what height is this? It's not the height he's jumping from.
Or
Remember?
it's the height inside the water.
It's the depth in the water.
Oh, yeah.
Okay. So, according to this, if I can increase that depth, I will increase the denominator. So let's just rewrite this, because there's now a h in both terms. So if I increase it here, it's going to increase this one and that one. So it's going to increase the force and decrease the force. So let me just rewrite it like this: half mass velocity I squared divided by delta h plus mass times gravity. Here they cancel out. So if I distribute this, okay, then I don't have one in the denominator anymore. So what will happen if I increase, what does this represent again?
The depth of the water.
In other words, how deep I dive.
Yes.
So if I can somehow dive deeper, the effect will be of the water will be less on me.
Yes.
So how can I dive deeper?
Like, do you mean if the distance of the depth of water is bigger, then the force you're going to encounter is going to be less?
Yes, but it doesn't have to do with how deep the water is. You didn't dive 15 meters and then hit the bottom. That's not what it meant. The water was much deeper than that. It meant he built 50 meters until his velocity stops. So if I can dive deeper, then I will be able to then the time it takes for me to stop is longer. So the force causing me to stop is smaller. So if I can dive deeper, the force causing me to stop will be less. So how can I dive deeper? By splitting the water. That's why you dive like this. You understand? You're kind of cutting through the water. You understand?
So by splitting the water.
Kind of splitting the water. You're not causing the water to directly hit your head, because then you're going to stop quicker. So you're kind of trying to be, is it aerodynamic? If it's in water. Or if you wear, for example, like this clothes. If I'm going to dive in this clothes, I'm going to get hurt, because the water will it will cause me to stop quicker. You understand? Because it's dragging, it's baggy. If I wear like what is it called? Those diving suits. They're very it's not aerodynamic. I don't know what it is in water, but in water they're very slippery, and that's why dolphins can go so quick in water, because their skin is so slippery over water. Understand? Dolphins can dive from a very high and they will go very deep, because the friction on their skin is less, so they dive deeper. Make sense? Okay. So we could dive deeper. That's another answer. What else can we see here? You said it, Bakani?
It's mass.
Mass. I can lose weight.
Yeah. So
Bakani, you will probably get less injuries than John, my friend next to you. Okay. Can we change gravity?
No.
No, unless you jump on the moon. Okay, but then. Do you understand why this is a level 4 question?
Yeah.
Here you have to have insight, you have to look deeper, you have to understand what factors will affect it, things like that. You have to make connections. So this is a difficult question to answer, because you have to have insight, and you have to have insight in physics. A lot of people say dive with your arms first to break the water. They have to explain to me from a physics perspective, why is that the correct answer? They got 1 mark, yes. You will get less hurt.
Yeah, but I heard that if you travel on a faster speed, then like you see how they design the.
Let's just quickly look at this. Which of the following is not in a state of free falling? What is free falling again?
Only gravity acts on the object.
Okay, a rock is broken off the edge of a cliff. A rock that has broken off the edge of a cliff. It's now falling. Is it in free fall?
Yes.
Good. a cricket ball after it is hit by the batsman?
It's gravity.
It's only gravity. A parachutist while gliding to Earth.
There's no gravity
No
in
one.
space.
No, a parachutist is someone that jumps out of a plane with a parachute.
Shoot is done. Okay.
But with him, there's gravity and some other force
And
acting.
some other force.
Yes.
So he's not in free fall. So he's falling, but there's
Not free.
there's friction. The parachute. No one got this correct.
Really?
A satellite orbiting the Earth. Everyone answered that one.
Yeah, because I was like,
Satellite.
yeah. You know, probably.
No. You know how they do satellites? Actually, how satellites work is satellites are always falling.
That doesn't make
Really?
They're always falling. The only point is that they've been sent into space. They've been rocketed out into space. So there they rocketed. Let's say this is the surface of the Earth. I should have actually drawn this with a different color so it looks like. Okay, so imagine now this yellow, the white part is the atmosphere. So what happens is they have shot the thing out into space, and now it starts falling. But as it's falling, the whole time falling, it was shot at such an angle that as it's falling, it's falling off the round side of the Earth. It keeps falling off the round side of the Earth. Does that make sense? So it keeps so it's shot, and now it's falling towards the Earth. It's falling towards the Earth, but as it's falling towards the Earth, it's still round.
So that's.
So I'm being attracted by the Earth. Yeah. So it has that direction, and it has a downward direction. Okay. And so its forward force and its downward force produces a net force. Okay. It's not forward and downward force. It's forward trajectory, and its downward trajectory ends up creating a net force, and that net force is tangent to the surface of the Earth. So that as it's falling, it's just continuing that direction. Because otherwise, if it was just moving, it would have just moved straight. You understand? But now there's an attractive force by the Earth the whole time, so it moves straight, and then it's pulled by the Earth the whole time, and it's moving straight, so that causes it to move in a curve.
Okay.
You get that? So for example, be driving straight, and all of a sudden there's a rope connected to a pole, what's going to happen to that car? It's going to start making a circle. See, there's now a force pulling it towards the center.
But is it
that
gravity?
pole. In that case, it's not gravity. It's so in other words, I've got a pole here connected to a car. Even if that car tries to drive straight in that direction, because it's connected to this pole, because there's an attractive force to this pole, he will start circling that pole. If his force is more than the force, the tension in that rope, it will go like this, but it will break. Does that understand? And then it will just go straight.
Okay.
But if these two forces are in equal, and if the force of the rope is more than the force he's trying to escape with, then he will be drawn towards the center.
Okay.
But if they are in equilibrium, if the two forces are equal, then he will travel around in a circle the whole time, and not unless that rope winds around the center. So that's kind of what's happening. But yes, they're in constant free fall. A satellite orbiting the Earth is in constant free fall, because the only force acting on him, the only reason why he's not going further into space is because the Earth is attracting him. There's no other forces acting on him. He doesn't have an engine or
But
anything.
you just said he's moving in that direction.
Yeah, because he was projected in that direction.
So
Understand?
The satellite is still moving in that direction.
It's still moving. So in other words, it was like he was shot into a certain direction.
But he will lose because of friction and drag and all this.
Yes, but he's not anymore. He's not anymore in friction. He's now in outer space. There's no air friction there.
Oh, okay.
There is slight friction, and therefore it has little. I don't know actually how it overcomes that slight friction, but yeah, in essence, it doesn't have any forces acting on it. It's literally the whole time falling towards Earth, but falling off the round side of Earth.
Oh,
Yeah, you can think of it like that.
Okay.
Okay, the second one. A ball of mass m hits a wall with a velocity of v.
These ones
and-
always get me, hey?
I don't know why. I know exactly why. I'll tell you why. Because you guys don't use signs. Everyone got the first two questions wrong. Everyone got the last question right. Okay. This question was a level 3 question. This question was a level 4 question. Actually, this is a level 2 question. This was a level 1 question. Everyone got level 1 question correct. And look at what I asked. I asked in question 1.2 is missing. In question 1.4, look what I asked. I asked what is the correct relationship between the work done, the net work done, and the change in
That's
kinetic
a
energy.
formula.
It's my formula. And they're equal. They're equal. As the one increases, the other one will increase. It's just this. The answer was A. Okay. Nevertheless, this question: a ball of mass m hits a wall with a velocity of v and bounces back at half the speed. What is the impulse of the ball doing at the bounce? So, how do we calculate impulse?
What do you say?
Impulse is what?
It's m into final velocity minus initial velocity.
Now, what is impulse?
Oh, it's
The
changing
change in momentum.
Momentum. In other words, it's future momentum minus initial momentum. What is the how do we calculate momentum? Is mass, which is
Times
just
velocity.
m, times future velocity minus mass times initial velocity. Now we know what the initial velocity was. It's just the mass is fixed, so you could have just taken mass out as a constant factor, common factor, and then we know what initial velocity was. What was initial velocity? They told us initial velocity is the ball hits at a speed of v. So what is initial velocity? V. It bounces back at half the speed.
So
What?
half v.
No. What is
bounces
future
back.
velocity? Sorry?
It bounces back at the speed of half the original one.
Very important, it bounces back.
So it's negative.
It's negative
Oh.
half. Half. And so you get,
It's gonna be 3 over 2.
so it's negative 3 over 2 mass times velocity. So if we go back to that, which one is it?
See.
See, 3 over 2 mass times.
I was going for like the horrible choose.
Really, if something bounces back,
It goes with the
you
negative.
always have to put that negative in. There was an question like that in the exam where a big guy runs into 3 guards
Yeah.
and he runs with them and then he lets go of them and they bounce against the wall and they bounce back, and the question asks what is the force that they experience against the wall, and net force is equal to change in momentum over change in time. Their change in the momentum is their mass times their future velocity minus mass times their initial velocity. And you have to remember that their future velocity and initial velocity is in the opposite direction. And that will cause this to become a plus.
Okay.
Okay, because otherwise, let's say their momentum, because remember their momentum is a vector. They have momentum in that direction and now their momentum goes in this direction. So let's say they started with a momentum of 10 kilogram meters per second. Okay, let's say they started by that, and then when they come back their momentum is 5 kilogram meters per second. What is their change in momentum?
5.
No. 15. Because they're coming back at negative. What's the difference between 5 and negative 5? 15 kilogram meters per second. So if you just say 10 minus 5, you get 5 meters per second, kilogram meters per second. Okay, you get it? So very important, consider your signs. Okay, so this question is a collision question. Okay, you're saying, well, most people did it fairly well. I'll just answer some question. I'm not going to do it because I'm looking at that other formula. You can't use that formula with collisions. Okay. If Usain, and it's talking about Usain Bolt, the fastest man in the world, 94 kilograms. His highest speed, recorded speed was 48 kilometers per hour. That is incredibly fast. Okay, he's not the fastest living thing though. The fastest living thing is the peregrine falcon. That's 1.5 kilogram mass. The peregrine falcon can reach speeds of up to 320 kilometers per hour. This falcon goes so fast because he dives out of the air and dives towards the earth. So what gives him that velocity is actually the gravity of earth. If Usain and the peregrine falcon are heading directly towards each other at their top speeds, what is the total momentum of the system before they collide? And again, people make the same mistake. Probably about 25% of the people didn't consider that they are heading in opposite directions. One of the two must have a negative velocity because they're heading in opposite directions. Make sense?
Yes.
So if they're heading towards each other, the total momentum will be less because you're subtracting them from each other than if they're heading away from each other. Okay, or heading in the same direction. Yeah, if they're headed away from each other, it will be the same as when they're heading towards each other because they're in opposite directions.
Yes.
If they're heading in the same direction, their total momentum will be more. Does that make sense? Okay, state the theorem of conservation of linear momentum. The two collide. With our calculations, predict in which direction the two will be heading after the collision. Now, you obviously look at which one has the highest momentum. The peregrine falcon or now when you do this first calculation, you're adding their two momentums. So you've calculated both momentum. Or you just look at what is the answer in question 1. If you chose Usain's direction as positive and you get the total momentum is positive, it means the final momentum when they're together must also be positive, which means it must be in the direction of Usain. Does that make sense, or did I speak too fast? If you choose the Usain is positive, but you get the total momentum is negative, then obviously the final momentum must be negative as well, which means they will be heading in the peregrine's falcon's direction. Make sense? So without calculations, just based on question 3.1, you would have been able to predict that, or without calculations. Okay, what will the magnitude of their combined velocity be directly after they collide? That's normal momentum calculations. I don't want to go into that. If the change in Usain's momentum happened in half a second during the collision, what is the force exerted by the falcon? Okay, that is the one I said for moderation. So all of those errors it was fixed. So he's asking what is the force that Usain is experiencing. So it's change in momentum over change in time. Now, just important, this is not the change in the momentum of the system. The change in momentum of the system, it doesn't change. it's Usain's change in momentum. So we'll take Usain's mass times his initial velocity, final velocity, minus Usain's mass and his initial velocity divided by delta t. If I took and the initial velocity would be the velocity he has just before the collision, and the final velocity is the velocity he has after the collision, but after the collision it is the velocity that he and the Falcon has together, which you worked out in the previous question. I want to go to the next question, which everyone struggled with. So, but I also want to mention that my control test was very difficult. I did make it difficult. I didn't set the June exams. I don't think they were difficult at all.
Who said it?
It was actually last year's prelim exam. Okay, it was a very interesting question though. The Seawise Giant is the longest ship ever built. She was 458.45 meters long. And there's a physics thing that never had any information that wasn't used. With a mass of 260,941 tons. The steam turbines had a maximum power output of 50,000 horsepower, another thing that wasn't necessary for the question. According to her captain, S.K. Mohan, she could reach up to 8.5 meters per second in good weather, and it took 9 kilometers to stop from that speed. So here they say, according to the statement by the captain, how long will it take the Seawise Giant to stop from its maximum speed? You could use my formula, but in this case it would just be too complex. Not too complex, it's simpler than that. Because I have initial velocity. So let's just write what I have. I have initial velocity. She starts at 8.5 meters per second. I have final velocity, because it's asking me how long does it take to stop, which is 0. And I have how far it takes her to stop, delta x. Okay? Actually, let's use my formula doesn't have t in it. That's a shame.
So if they say she could reach up to, isn't that final?
Yes, so so in other words, that is the maximum velocity she could have traveled at. So it's just giving you information about the ship.
Okay.
It's saying she can reach speeds of up to 8.5 meters per second. So it doesn't mean that she is trying to get there.
Okay.
It means that's where she could get to.
Okay.
And now it says, how long will it take the Seawise Giant to stop from its maximum speed? So it's traveling at its maximum speed, the speed it could reach. And then how long does it take to stop from that speed? And all we have to go on is that the maximum speed is 8.5, stopping means 0, and the distance it takes to stop is 9 kilometers. That's far. Like you start slamming on brakes, 9 kilometers later you stop. That's like starting braking here and stopping at my house. Anyway, that is 9 kilometers, which is 9,000 meters. So we simply use that future velocity squared is equal to initial velocity squared minus, no, there's another one. We'll use that delta x is equal to average velocity, which is initial velocity plus future velocity divided by 2 times time. Okay, so this is 9,000, is initial velocity is 8,5. Final velocity is 0 divided by 2 delta t. Are you there yet, Bakani?
Yeah, it's 2,117.65.
Okay. Seconds. We divide that by 60.
It's 35.29 hours.
35.29.
Yes.
29. It's not hours, it's minutes. Okay, so more than half an hour for it to stop from that speed. Okay. And the reason why it takes so long to stop is because of her mass. That amount of mass, her momentum is so much that it will take just so much to stop her. Remember, momentum is a measure of how difficult it will be to stop you. Okay, now, if drag force, frictional force in the water is ignored, look at that, frictional force in the water, lovely. Show what the power output of this, show that the power output of the steam engines to bring the Seawise Giant to a stop. Actually, I'll change this question later by actually giving you the power output that you should get. This was the question when I sent it for moderation, then we just made it a little bit easier. Actually giving you the power output. Now the power output is the power applied. So it's work applied divided by delta t. So here's delta t, we've calculated delta t. We just need work applied. And what are we going to use? Formula. Net work done is equal to change in kinetic energy. What are incomes in this case? So it's traveling, and we're trying to... Frictional force is an income, well done. No, it's not an income, because it's still...
Frictional force is always an expense.
Always an expense, always against us. But they tell us, but well done, it's good you think about it. Frictional force in the water can be ignored.
Okay.
We ignore frictional force, so that's not going to be... Okay, is gravity at all at work here? Not when I'm traveling on a surface, on water surface, definitely not. Okay, so no, gravity is not at work. So what's the only other force?
It's kinetic friction.
Sorry?
It's kinetic. It's kinetic friction.
No, they said we can ignore friction.
In the water.
Yeah, but the kinetic friction comes from the water.
Force applied, maybe?
Force applied is the only... What is force applied, an income or an expense? What is the force that's being applied doing?
Income that's going that way.
If
it's horizontal, isn't it?
It's horizontal, so it's traveling in that direction. Okay.
Isn't
the force applied be? What would apply a force in this case? In the case of a boat, what is applying a force?
Engine?
The engine.
Yeah.
It's turning the propeller.
Yes.
Now, in this case, we call the engines, these are called steam turbines. They are the engines in these massive ships called steam turbines. So in other words, they are trying to stop it. So it is an expense. So in other words, the net work done only consists of negative work applied. Is equal to the change in kinetic energy, which is half the mass times future velocity squared minus half the mass of initial velocity squared. And we just want the value for work applied. So we'll take half the mass. The mass is given in tons, but we must multiply tons with another.
So to stop it, they use another power, not just brakes like in a car.
They don't have brakes in the boat, obviously, because in a car, what causes us to move is our wheels. So what we do is we stop the wheels from turning, so we slam on the brakes. In a ship, obviously, a lot of what causes the ship to stop is the drag of water. That helps a lot to stop the ship. If you just switch off a boat that's traveling on the water, the engines, you'll see most people when they go out in the ocean or whatever, when they want to stop, they just switch off the engine and then they stop. Why? Because the friction of the water against the boat. But now they're telling us we should ignore it and show that if we ignored that.
So they're applying a force backwards.
So now these are propellers propelling it forward. Now what the propellers are doing, they're going in the opposite direction. And that is now working against that movement. Okay, so but all of this is it just helps to understand what's happening there, but it doesn't take away from the fact that we are trying to work out the power output of steam turbines to bring the Seaways Giant to the stop. So if something is causing something to stop, all I'm trying to work out is the amount of energy that thing is exerting to stop it, which is mean in the opposite direction. And then I can just ask, what else can I consider? Friction? Well, they said to ignore it. Gravity? Not at work here. See how simple that is. So the only thing it could be is work applied. Okay, which is what I want to use in my power. So that is 2.
And why did you say we could omit gravity on this one?
Because if something is traveling on top, a boat for example, a boat cannot go uphill. You understand? There's no uphill water or... Well, maybe... no, but the point of water is always horizontal, especially on the sea.
Yeah, but you're saying we should ignore gravity,
which is pulling it down, but it's not moving down.
Yeah, but it should. It should add on the friction.
Yes.
Which is what they said we should ignore.
We should ignore, yes. It will probably, because the gravity will pull it lower down, which will put more of the boat in the water. So there's probably a lot of factors you could consider that would have an effect. But that's probably why I just said ignore drag.
Okay.
So the future velocity is 0. Okay? The initial, so this first part of the equation, anyway, that doesn't even take part. So negative a half mass times initial velocity, and this should be 260,941 times velocity is 8,5 squared. Which just gives me work applied. What would that give me, please, the Bakani?
It's 9426.
9426
493
0.625. Okay, so let's not round off yet. And now if I have to work out power is equal to that work applied divided by 2117.65, which gives me
4451.
4451.
Yeah,
Point?
39.
4451.39. You sure? Then there's something. Oh, wait. We short another 3 zeros. I didn't multiply with. This was tons. I should work in kilograms. So just move that comma 2 more spaces for me, please. So it's 445139. 3 comma and not 2 more commas. 585, so 59 watts. Okay, sorry, everything was just multiplied with 1,000 because I forgot to multiply my mass with 1,000 because that was in tons. Okay, so I actually gave this value, and you should have reached that value using your calculations in the question I ended up using. Okay, but now the captain observed, however, that the actual power output to bring the sea-wise giant to a stop is much less than that. Explain what is responsible for the difference. So this is the calculation that we should have used. This is what the engine should put out. But when he goes and looks at the dials, he sees, but no, it's using much less than that. Why is the actual power used less than the calculated value, do you think?
Isn't it because they decreased the work applied?
How? So you're right. For this value to be less, the work applied must be less, because that can't change. When will work applied be less?
When
I want to show you here. On this side, this is the energy that we need to steal, isn't it? Because we need to change the kinetic energy from whatever it is to become zero. So we need to steal all of the kinetic energy. However, the only thing we considered to steal energy was the engines. But in reality, that's not the only thing stealing energy. Okay? The reason why the observed power of the engines is less than that is because we ignored friction. But in reality, you're not going to ignore friction. Do you understand? So in other words, the actual power output to bring the sea-wise giants to a stop is much less. Explain what is responsible for the difference. So for example, when we do calculations, or not calculations, experiments in physics to test something, like we want to see if momentum is conserved, and then we find, oh well, momentum wasn't conserved. Why wasn't it conserved? It's a law, it has to be conserved. Why wasn't it conserved?
sometimes friction.
Because we assume there's no friction. So we have to make assumptions in order to do calculations. So if our calculations don't work out, it means our assumptions were wrong. So this is basically, and again, this is a level 4 type question. You need to understand the nature behind science. That when I actually have different observations than calculations, the error lies in my assumptions. And the only assumption I had here was that there's no friction. Which means, but there are friction. And friction will help me to stop the engine, so the engines don't have to work so hard. Make sense? And an answer like that would work. Cool. And that was it. People didn't do too bad in this test. We've got an average of around about 50%, which isn't bad for a really difficult test.
For the whole school, is that the average for the whole school?
Yeah, for everyone.
Gee, that's good. Wow. Good bad.